We hear it all the time, that our world is three-dimensional. It makes sense after all. We can only define up to three directions, each at a right angle to each other, that don't interact with each other. No matter how far left or right you go, you won't move up at all. But the moment we try to add another dimension into the mix, it all breaks down. No matter how hard you try, in our three-dimensional universe you can't lay out four or more directions that won't interact. Now I know what some people are thinking. Can we consider time a dimension? In simple terms, it does make sense. We can measure time and tell one point in time from another in a linear sense. 4 hours later is always 4 hours later, just like how 4 feet to the left is always 4 feet to the left. Heck, you could even make time act like a spatial dimension. Take a flipbook. Each frame of animation is a two-dimensional image, but by traveling through the 3D stack of these two-dimensional frames at a consistent rate, we can make time act like a spatial dimension, where height in the stack of 2D frames is the same as time between two events. In that sense, this 2D animation just became 3D, right? Not necessarily. Just because time can match up with a spatial dimension doesn't mean that it is one. Notice how in the animation, time only moves one way, from the bottom of the stack to the top, but in regular 3D space, one can move either way, up or down. This doesn't mean it's wrong to imagine time as a spatial dimension, since it clearly can be done, but rather it's wrong to assume a spatial dimension and time are exactly the same. So now that that's cleared up, what would four-dimensional space be like? The easiest way to answer that question is actually to do the opposite. Rather than add a dimension in, let's take a dimension out. Try to picture what it would be like to live on the surface of a sheet of paper. You can no longer jump up or down off the paper because up and down don't exist to you anymore. You can't look up off the paper either. All you can do is look forward across the paper. When you do look in front of you, you'll see a horizontal line, and in that line you'll see the edges of other 3D figures. Imagine a circle in a box. Clearly, to us, as three-dimensional beings, we can see the circle in the box, but to a two-dimensional being, the sides of the box would prevent anyone from seeing inside. Also consider that whenever something casts a shadow onto, say, a wall, the shadow forms a line on the wall. Of course, to you, all the walls would be lines anyways, so you wouldn't really notice. Let's bring that same situation into 3 dimensions. As you look around, all you can see are two-dimensional objects, just like how even the box in 2 dimensions looked like nothing more than a line. Since you can only view it from one side at a time, the front of the box in 3 dimensions only looks like a square. Also, suppose the ball is still in the box, but now it's a sphere inside a cubic box. We still can't see it now because all of the sides are still covered. The shadow the box casts on the wall looks different. Instead of just being a line like before, now it's a flat 2D shape. If you wanted, you could even trace it onto paper and get a 2D drawing out of it. Here's where things get tricky. Let's try to add a new dimension that we haven't ever seen before. Let's just dip our toe into the 4-dimensional water and use the differences between 2D and 3D space to determine what would happen in 4D space. One of the first things you would notice if you looked in a 4D space is that you would see the world as a 3D shape, in a similar way to how you view a 3D world and can put it onto a 2D picture. But there's one catch. You can see all the sides of a shape. Remember how if you were to put a circle in a 2D box, you could still see it looking down from above in 3D? Well, now in 4D, you can see every side of the 3D box when looking down on it, including seeing the ball inside. Are you freaked out yet? After you get over the bit of wonder you experience being able to see inside of the box, you might also notice that another 4D box is casting a shadow on the wall. And the shadow, it's a 3D shape. Yes. Just like how 2D space has linear shadows, 3D space has 2D shadows, here in 4D space we have 3-dimensional shadows. What would one of these shadows look like? Here's an example. This is called a tesseract, which is the shadow you would get from casting light through a 4D cube. Notice how it's made of 2 cubes connected at the vertices, just like how you can draw a cube on paper from 2 squares and connecting the corners. Now the tesseract looks weird enough sitting still, but watch what happens the moment you start rotating it. I'll give you a moment to clean up your mind, which is most likely at this point exploded. Yes, that's what the shadow of a 4D cube looks like when the cube rotates. Why does it do this, where the middle cube stretches out to become the outer cube? Let's take a look at the shadow of a 3D cube. First, note the 2 squares. One is smaller than the other because of perspective, making further objects appear smaller. But if you follow the small square, you'll see that it moves to the other side, before eventually moving to the front of the cube and becoming the big square. Now watch the tesseract again. The little cube, because of 4D perspective, when rotated to be closer, becomes bigger, while the big cube rotates to be smaller. So just like in a 3D cube, where the big and little squares switch places, in a 4D cube, the big and little cubes will switch places. All in all, 4-dimensional space isn't all that bad. In fact, with the proper understanding of what will happen, one can devise some clever shapes that do things we can't even imagine doing in 3D space. Ever hear of a Mobius strip? It's a plane that, thanks to being bent around in 3D space, has only one side, because what would normally be the top and bottom sides are now connected, making them the same. Thanks to a little 4D trickery, a figure called a Klein bottle can exist, where the inside and outside are the same. Ever notice how you can mirror writing on a page by flipping it over? In 4D space, you can mirror a whole 3D object just by flipping it over 4-dimensionally. 4D space shows us what is arguably the best part about mathematics. It works regardless of your bias. In a previous video, I showed how we could use 2 digits to represent any value that 10 digits can. And in a similar way, just like how we can do any mathematical function possible in base 10 in base 36, we can have geometry that functions consistently, whether it has 3 dimensions, 4 dimensions, or possibly even more.